Hello everyone. Today we continue with computer system architecture course and our topic is program control. In the last videos we discussed general register organization, stack organization, instruction formats, addressing modes, and the last video was on data transfer and manipulation. Program control instructions specify conditions for altering the content of the program counter, while data transfer and manipulation instructions specify conditions for data processing operations. Instructions are stored in memory in successive memory locations. Each time the instruction is fetched from memory, the program counter is incremented by 1 or updated if the instruction is stored in more than one memory location, so that it contains the address of the next instruction in sequence. After the instruction is decoded, it will be executed and we start the next instruction cycle by fetching the next instruction from memory. Suppose that we have here the program, so instructions are executed one after another, and we can call this flow as a normal flow of execution. So the normal flow of execution will fetch and execute the next instruction in sequence. Program control instruction may change the address value of the program counter and cause the flow of control to be altered. So here we have a transfer of control instruction. Program control instructions are classified into branch and jump, subroutine instructions, and interrupt instructions. Branch and jump instructions may be conditional or unconditional. The unconditional instructions causes a branch to the specified address without any conditions, like the branch unconditional instruction in the basic computer or the go-to statement in the high-level languages. While the conditional branch instructions specifies a condition such as skip on positive accumulator, skip on negative accumulator in the basic computer, the if statement in the high-level programming languages. Here we have the typical program control instructions. First, branch and jump, and they have the same effect, except that they are used to denote different addressing modes. Usually the branch is a one address instruction. The skip does not need an address field, so it is a zero address instruction. The conditional skip will skip the next instruction, here the next, if the condition is met. So if the condition is true, we will continue to this instruction. And this is done by incrementing the content of program counter by 1. When this instruction was fetched, the program counter was updated to point to this instruction. So if the condition is false, we will not skip this instruction and we will continue as usual. The call and write instructions are used with subroutines, and we will come to them later in this chapter. Next, the compare and test instructions does not change the program sequence directly. The compare instruction, for example, compare AB, performs the subtraction A minus B, and the result is not stored anywhere, and the values of A and B are not changed. But the flags like the carry, sign flag, Z flag, or B flag are affected. So in the next instruction, we can use the values of these flags as conditions. While the test instruction, for example, XY, performs the logical AND operation, and again, the result is not returned anywhere in the arithmetic logic unit, and the values of XY are not changed. So these two instructions affect the flag values only. The four status bits are the carry flag, the S sign flag, Z flag, and V overflow flag. The bits are set or cleared as a result of an operation performed in the arithmetic logic unit. Suppose, for example, we have the two unsigned numbers and we are adding them 1, 1, 1, 0. So here the carry flag is 0. We haven't carry. The sign flag is 0. The Z flag is 0 since the result is not 0 and we haven't overflow. It is sometimes convenient to supplement the arithmetic logic unit circuit in the CPU with a status register where status bits conditions can be stored for further analysis. This is the block diagram of an 8-bit arithmetic logic unit with a 4-bit status register. The 8-bit numbers A and B are applied to the arithmetic logic unit A0 through A7, B0 through B7. The result F0 through F7 is available at the output. Here we have a circuit to check if the result is 0. In this case, if the result is 0, the Z flag is set to 1. F7 from the result is applied to the sign flag. Carry out is applied to the carry flag. And for signed numbers, the carry to the sign bit and the carry from the sign bit are exclusive OR and applied to the overflow flag. If the exclusive OR is 1, then we have overflow. Otherwise, we haven't. Again, the carry bit is set to 1 if the end around carry or carry 8 is 1. It is cleared if the carry is 0. The sign bit is set to 1 if the highest order bit F7 of the result is 1. Otherwise, it is 0. The 0 flag or Z flag is set to 1 if the output of the arithmetic logic unit contains all zeros. It is cleared otherwise. Bit V is set to 1 if the exclusive OR of the last two carries is equal to 1 and clear to 0 otherwise. And this is the condition for an overflow when negative numbers are in 2's complement form. The status bits can be checked after an arithmetic logic operation to determine certain relationships that exist between the values of A and B. For example, if Z is set to 1 after an exclusive OR operation, it indicates that A is equal to B, since A exclusive OR A equals to 0. If bit B is set after the addition of two signed numbers, it indicates an overflow condition. And for example, we can compare the two operands A and B. And after that, check the values of the flag bits to determine if A equals B, or A greater than B, or A is less than B, and other conditions. And I'll come to this case in more detail later in this video. A single bit in A can be checked to determine if it is 0 or 1 by masking all bits except the bit in question and then checking the Z status bit. Suppose, for example, that A equals to 1101, and here we have X unknown bit 011, and here the bit to be checked. We can do that by first masking A, which is 1101,011, with B, which has all zeros in all other positions, and masking is the AND operation. So now we have here 0, 0, 0, 0, 0, 0, 0, and here X. In this case, if X was 0, then the Z flag will be set to 1. And if it was 1, then the Z flag will be 0. So according to the value in the Z flag, we can continue to the desired action. Next, conditional branch instructions. Each mnemonic is constructed with the letter B for branch, here, and an abbreviation of the condition name. When the opposite condition is used, the letter N for no is inserted to define the zero state. For example, BZ branch if 0. If the Z flag is 1, then the condition is true and we branch. But a branch if not 0, we check the Z flag. If it is 0, we branch. And branch if carry, here, we branch if the carry flag is 1. Branch if no carry, here, checks the carry flag, and if it is 0, we branch. So we branch if we haven't a carry. The zero status bit is used for testing if the result of an ALU operation is equal to 0 or not. The carry bit is used to check if there is a carry out of the most significant bit position of the ALU. It's also used with the rotate instructions. The sign bit reflects the state of the most significant bit of the output from the ALU. The overflow bit is used when we are dealing with signed numbers in two's complement representation. This group of instructions is used for unsigned numbers, and this group is used for signed numbers. For unsigned numbers, we use branch if higher or equal, branch if lower or equal, if not equal. But for signed numbers, greater than or equal, less than or equal, and branch if not equal. Please note here, the conditions are the same, but the flag bits tested are not the same. Suppose, for example, we have the two 8-bit numbers A and B. The compare instruction AB performs the subtraction A minus B. And this is done by adding A here to the 2's complement of B. And this is the result. The computer performs the same operations if the numbers are signed or unsigned. In this case, since we have carry here, the carry flag is set to 1. The sign bit here is 1. And since the carry to the sign bit is 1, and from the sign bit is 1, and the exclusive OR of these bits is 0, then the overflow flag is 0. And since the result here is not 0, then the Z flag is 0. If we consider these numbers as unsigned numbers, A equals to 240 and B equals to 20. So the operation performed is 240 minus 20, which is 220, and everything is okay. Here we have that A is greater than B and A is not equal to B. These two relations can be derived from the fact that the status bit C is equal to 1 and Z is equal to 0. The instructions that will cause a branch after this comparison are branch pair or equal, and a branch if not equal. Now suppose that these numbers are signed numbers. Again, the compare AB performs the subtraction by adding A to the 2's complement of B, the same result as in the previous case. Here the carry flag is 1 again, and the S flag is 1. The B flag is set to 0, and the Z flag to 0. But number A as a signed number is minus 16, and number B is 20. So our operation is minus 16 minus 20, which is minus 36 here. Since minus 16 is less than 20, we have that A is less than B and A is not equal to B. And these two relations can be derived from the fact that the status bits is equal 1, negative, B equals 0, no overflow, and Z equals 0, not 0. The instructions that will cause a branch after this comparison are branch if less than, branch if less or equal, and branch if not equal. The relative magnitude of two unsigned numbers can be determined after a compare instruction from the values of the status bits C and Z. The relative magnitude of two signed numbers can be determined from the values of S, V, and Z. So for unsigned numbers, we have to use this group of instructions, and for signed numbers, this group of instructions. Next subroutine call and retain. A subroutine is a self-contained sequence of instructions that performs a given computational task. During the execution of the program, a subroutine may be called to perform its function many times at various points in the main program. The instruction that transfers control to the subroutine is known by different names. In the basic computer, we have the branch and save retain address. In some programming languages, the call statement is used, or jump to a subroutine, or branch to subroutine, and others. A call to a subroutine XX transfers control to the subroutine. We encounter a return statement, control is transferred back to the statement that follows the subroutine. The call to a subroutine instruction performs two operations. First, we have to save the return address, which is the contents of the program counter, and control should be transferred to the beginning of the subroutine. The last instruction in the subroutine returns control to the calling program by transferring the return address into the program counter. So when the call to a subroutine instruction is executed, we first save the content of the program counter. Then we load the address of the subroutine into the program counter, and we start a next instruction cycle. When we encounter a read statement, we have to restore the contents of the program counter and start a new instruction cycle. Next, where to store the return address. In the basic computer, it was stored in the first location of the subroutine. It can be stored in a fixed location in memory, or we can use one of the processor registers to store the return address, or in a memory stack. And this is the most efficient way. The call statement in this case performs the push of the return address into the stack, and the read from the subroutine statement performs the pop of the return address from the stack into the program counter. A subroutine call is implemented with the following macro operations. We decrement the stack pointer, then we push content program counter onto the stack. Yeah. Then the effective address is loaded or transferred to the program counter, causing a transfer to the first statement in the subroutine. Now we have the return address in the stack. And the return from the subroutine is implemented using the following macro operations. The content of the memory location addressed by the stack pointer is popped into the program counter, and the stack pointer is incremented by 1. Using stack, we can call a subroutine from a subroutine. For example, call subroutine 1. Here we have subroutine 1. From this subroutine, we can call subroutine 2. And here we have read. Here subroutine 2, etc. And here we have read. So when we call subroutine 1, return address 1 is pushed into the stack, and we start subroutine 1. Here, when subroutine 2 is called, return 2 is pushed into the stack, and we continue to subroutine 2. When we encounter the read here, this return address is popped from the stack. So control is transferred to this statement. And when we encounter this let statement, this value is popped from the stack and control is transferred here. By using a subroutine stack, all return addresses are automatically stored or pushed by the hardware in one unit. The programmer does not have to be concerned or remember where the address was stored. Using a stack to implement the subroutine calls and returns, it's also possible to implement a recursive subroutine, which is a subroutine that calls itself. And this was not possible if we, for example, use one register to hold the return address. Next, program interrupt. Program interrupt refers to the transfer of program control from a currently running program to another service program as a result of an external or internal generated request. Control returns to the original program after the service program is executed. By using interrupts, the CPU executes the instructions without the need after each instruction to check if any of the input-output devices needs a service. If any of the input-output devices needs a service, then it interrupts the CPU. And in this case, the CPU should save the return address along with other information and branch to an interrupt program, or also known as interrupt service routine, to service the I/O device. After completing, control should be transferred back to the main program. The interrupt procedure is similar to a subroutine procedure, except the interrupt is initiated by an internal or external signal and not from the execution of an instruction as in a subroutine. The address of the interrupt program or interrupt service routine is determined by the hardware. In subroutine, the address was defined in the instruction. For example, call subroutine 1, the name of the subroutine. And the last thing, in subroutines, we need to save the return address only, which is the contents of the program counter, while interrupt procedure should store all the information necessary to define the state of the CPU. So in the interrupt, we need to store the return address, the processor registers, and the contents of certain status bits, along with the additional bit called the mode bit that defines the user or supervisor mode. Regarding the status bits, all the status bit conditions are usually grouped into one word called program status word, and usually are stored in one register called program status register. So in the case of interrupt, we have to store the program counter, the processor registers, and the program status register and the mode bit. There are three major types of interrupts that cause a break in the normal execution of the program: external interrupts, internal interrupts, and software interrupts. External interrupts come from input-output devices, a timing device, from a circuit monitoring the power supply, or from any other external source. Internal interrupts arise from illegal or erroneous use of the instruction or date, and they are called traps. External and internal interrupts are initialized from signals that occur in the hardware of the CPU. A software interrupt is initiated by executing an instruction. Software interrupt is a special call instruction that behaves like an interrupt rather than a subroutine call. It can be used by a programmer to initiate an interrupt procedure at any desired point in the program. When the program is executing, we say that we are in the user mode, and the mode bit is set to the user mode. When an operating system or supervisor program is running, then we are in the supervisor mode, and the bit should be in the supervisor mode. When the operating system transfers control to the user program, this bit is switched to the user mode. When the program is terminated, the control returns back to the operating system, and this bit should be switched to the system mode. Instructions performed in the supervisor mode are called privileged instructions. If, for example, we are running the program in the user mode, and here we have an error, for example, division by 0. In this case, we have an internal interrupt called trap to the supervisor that should take actions to solve the problem. In this case, one solution may be abnormal termination of the program. So this is an internal interrupt called trap. Another example, suppose we are running the program and we have a read or write to a file operation. This instruction behaves like a call to a subroutine. So the control switches from user mode to supervisor mode, and we have to store the return address along with the registers and the status bits. Now the input-output operation is performed in the supervisor mode, and when completed, control is returned back to the program. We'll discuss interrupts and their types and the actions taken by the interrupts in more detail in the operating system course, and this course is required for all computer science and engineering students. For today, that's all. Thank you.